Okay, so, like I said, work backwards. So what reagent would you use to, first of all, what is that functional group? It's an epoxide. Or if you're from Oklahoma, it's an epoxide. Small town Oklahoma, sorry.
Every town is small in Oklahoma.
True enough. Total, I'm just going to have a conversation with you now about Oklahoma instead. All right, so how do you make an epoxide? MCPBA and an alkene. So there's this arrow that is, I'll explain it in a minute. So this is called a retrosynthetic arrow. I am not going to use it, but you might see it next semester. It's a big fat arrow and it points the wrong way. So what that arrow is telling you is you can make that compound from these things. So like I said, retrosynthesis is the classical way to solve these synthesis problems, right? It's hard to start at, and people have done total syntheses of hundreds of steps, right? I'm going to make some gargantuan natural product, and I'm going to start with, petroleum. Okay, so being able to think backwards, there's no way to, start with hexene and make your way up to Taxol logically. So you start with Taxol and like, well, what would I do to get here? And then you work your way back. Okay, so this alkene and MCPBA would make the epoxide. Now do the same thing. And what I would recommend in these, as you learn to work synthesis problems, is you sort of at every point you go back a step, you look at the starting material, the thing you're told to start with, and ask yourself, do I know a reaction that will take me from the thing I'm supposed to start with to that? And the answer here is you don't. Right? There's no single reaction that would do that. So what reactions have you guys seen that would make an alkene? An elimination reaction. And so now you've got a whole bunch of possibilities. You could do all the different possibilities. You could do this from an alcohol, and you could do either alcohol here, right? You could use a halide. Right? And the halide or the alcohol would have to be on one of the two alkene carbons. So sometimes your retrosynthetic, it could be possible that I'm not going to get one answer from you guys. If I gave this on an exam, I'm going to get, let's say everybody gets it right on the exam. I still could have 6 or 7 different answers. All right, so can you make any of these from the thing that you start with? Top right one. What's the reaction? Yeah. So this retrosynthetic arrow, and actually here, I'm going to write E, right? And this is the thing. There's a whole bunch of different ways to do elimination. I should have said that before I did the last step, right? You can do, with an alcohol, you can do an acid catalyzed dehydration. So that would just be sulfuric acid. Since we're getting this is going to be the Zaitsev alkene, the more stable alkene, the more substituted alkene. That would be the one that you would expect to get. Or if you use a halide, it could be E2 or E1. If you do E2, you want to avoid getting the Hoffman product. So boiling aqueous hydroxide would do this. All right, so this other one then, the radical reaction, this would be Br2 and light. Make sure you write light there, or if you want to just write Br2 and radical. So this is the other thing, at least when I do synthesis problems. And my plan for Thursday is to give you a synthesis problem like the day before and have you guys come to class having thought about it a little bit. Probably give you 2 or 3 of them. It's also a good way to review reactions. But when you don't necessarily have to give me, like let's say you had done this but you cannot remember what MCPBA. You know you can turn an alkene into an epoxide, but you cannot remember the letters MCPBA. You could write epoxidation, right? Same thing here. You could just say elimination. I don't remember the, like that might be a deduction. If this is say a 10-point problem and you just write, I know there's a reagent that makes an epoxide, but I can't remember it. Maybe I take off a point, but you saw the synthesis, right? Okay. Yeah, so if you do this, this X turns into a bromine. So now we might, well, let's leave that X. So let's write out what you would actually do here. So we would start with our alkane, Br2 light. We get the bromide, and then I would probably use methoxide, methanol. Doesn't matter the temperature here. How come?
Tertiary.
It's tertiary. Tertiary bromide can't do an SN2 reaction, so this is going to be, has to be an E2. Like if I use this bromide, it would matter maybe. Still secondary, it's pretty hindered. But you'd definitely want to give a temperature. So this is going to be an E2. We get this alkene, and then MCPBA gives us the epoxide. Neat little three-step synthesis. All right. So, like I said, sort of think forward and think backward at this point in your life. Thinking forward, if you're trying to actually make a molecule in the laboratory, is hard. Right? If I just sit down with a starting substrate, and I'm like, okay, all of organic chemistry is open to me now. There are thousands of reactions. I can do all sorts of stuff. Thinking backwards sort of narrows your focus down.
What's the difference between using NBS and BR2 for making a
Good.
tertiary alkane?
It's a good question. I don't think I mentioned NBS in class. Okay, I'm gonna, there's a sentence I was about to say, I'll say it at the end of this. So the same thing over there, if you were to do, okay, so NBS and light, or instead of light, a peroxide and heat. NBS is N-bromosuccinimide. It's this molecule. And I cannot think of this reagent without the word damn it associated with it. Because when I sat where you sit, I never could remember what this thing did. And so, anyway, you can follow the story from there. So this is going to just give us, that's it, right? What it does, what NBS does, how you should think of it, is that it's a Br2 source. It actually does make some Br2 in solution. Pretty much any of the reactions that you think of Br2 doing, you can use NBS. And it's arguable why you would want to do this. So one reason, solubility is always an issue. Right? NBS is nicely soluble in organic solvents. Br2 is really as well. Br2 is a much more hazardous substance to work with. It's a really volatile liquid. You know, I've asked you guys if you've seen iodine. Anybody seen Br2 bromine? It would be really unusual if you had. It's this super dense orange-red liquid. And when you open it up, you can see fumes coming off of it. And so it's hard to work with. And it's pretty toxic. So NBS is a nice, it's an orange solid. You can weigh it out, it just sits there. It's a lot easier to stoichiometrically add NBS than Br2. There's another, in the field of organic synthesis, there has come to be another measure by how efficient a process is, which is not necessarily yields. So like a lot of times when you hear the word efficiency associated with a synthesis, It's yield. All right, let's say this reaction goes in 90% yield. This reaction goes in 95% yield. And this reaction goes in 80% yield. Those would actually be three really nice yields. What's the overall yield? Yeah, you can use, in fact, I will use 80. I can't do this with 80. Good answer.
Is it like 85-ish, like the average of them?
It's not the average.
68.4.
68.4. Your phone and my phone do the same thing. So, yeah, you just multiply 0.9 times 0.95 times 0.8. So this is a three-step process. You're down 30% of your material. All right, so if you have, it's the longest synthesis I've done. I think I did a 12-step synthesis once. You know, so like 0.9 times 0.9 12 times is not very much. And seriously, most reactions that you're going to do, and like everybody, you guys go in the teaching lab and you get like a 98% yield, and you're like, oh crap, it's not 100, they're going to fail me. Like most reactions you do not go with anything like that kind of yield. There's just physical loss, especially on a small scale. If I'm working with 5 milligrams of material, and you know I leave half a milligram on the vial or on a spatula, which is not hard to do, that's 10% of my material. Okay, so you can make a lot of money. I have good friends who've made very good careers just figuring out how to take a known synthetic sequence and maximize the yield and the loss. So, like if I have to do column chromatography on all these, now I'm talking about efficiency of time, right? So I've got to pay somebody to go in and do a column. People are expensive, which, okay, I'm going to not wander off into politics and economics, but this is one of the issues. Right? So actually, if you're a pharmaceutical company today, much more so today than when I was sitting where you sit, like you pay robots to do this. And a robot's expensive, but they work 24/7, right? They're pretty reliable. Their wives and husbands don't leave them, and then they're bad workers for 6 months. So like, robots are nice. But politically, that's terrible, right? Because now we've put somebody out of work. Anyway, that is what efficiency, I keep saying, like when I sat where you sit, that's what we meant by efficiency. What are the yields? How quickly can we move one step to the next? Is it easy to purify the intermediates? So if I look, I might choose to do a 5-step synthesis over a 3-step synthesis because I can basically just do an aqueous workup, all 5 steps, take that crude product right into the next reaction. I never have to purify anything. I might do 5 steps instead of 3 steps because the reagents are cheaper or easier, less harmful to the environment. The other efficiency we have today that we've come to think about is atom efficiency. Look at this molecule. 6, 7, 8, 9, 10, 11, 16, 17 atoms in NBS. Plus or minus 2. Only one of them is going to do anything. Like only one of them is going into the product. BR2, 50% of the 50% of the atoms, maybe 100% of the atoms. In this particular reaction, 50% is going into the product. So using BR2 would be more atom efficient. We call it an atom efficiency. We don't want byproducts. As much as possible, you want all the atoms you put in the flask to go into the product. All right, so this is all beyond the scope of this class. And I'm not going to get to the last thing I was going to do, but we'll do it on Thursday. So all that's going to be beyond the scope of this class, but it's stuff you should think about. There's a lot of, like, the odds that any of you end up making a living under circumstances where you would need to know that MCPBA makes an epoxide from an alkene, pretty slim. All right, but that's true of 96% of your college education. Sorry, Dean Gillespie. All right, so most of the stuff, most of the actual details you learn in college, and it's worse actually in high school and junior high, you're never going to use. All right? So it's all a matter of thought process and solving problems. That's really what you want to focus on. But you're going to make, like I said, in that little synthesis over there, let's say that this epoxide you could sell for $10,000 a kilo. That'd be cool, right? So you would want to spend a lot of time. Now all of a sudden it's not an academic issue of how much do I leave on the spatula. Like that's a nice dinner out for 8 if I can get all that stuff off the spatula. And remember, you've got a robot doing this. Robot doesn't care if stuff cakes on the spatula, so you want it to proceed quickly. There are a lot, that's a really specific example. Most of you are going to end up, well, those of you who don't become doctors, you're going to do the same thing doctors have always done. But if you're working in the chemical industry, that's the kind of thing you wind up doing. There's a handful of people who wind up trying to discover new reactions, and that's a lot of fun. But even in a pharmaceutical company, that like, hey, my team invented this new drug, super wonder drug. Here's something that's never been cured. Somebody's got to figure out how to make enough of that for 8 billion people, right? So we're reading about this right now. Follow the vaccine trials, they're really cool. Not the trials necessarily, but the development. There's a lot of new technology going into that. But if you haven't followed what so Pfizer's vaccine has to stay below -80 the whole way. So think about doing that. We're going to make that in Belgium, and we're going to try to get that to New Zealand somehow, and it's got to stay below -80 the whole way. Right? You can figure out how to do that, you're going to make a good living, and like help people and stuff. Yeah, I have none of that was in the notes today. What any questions before we go?
Are we gonna have to do like a backward synthesis on the exam?
I don't know yet. I've got a few days to figure that out. Yeah.
So the only mechanism we would need to know out of those 3 would be the second one?
Oh yeah, so one thing, and if you look at old exams, there might be sometimes, we're getting to it. If I'd been able to do this last week, clearly it would be on exam 3. If I didn't get to it until Thursday, clearly wouldn't be. This is like hard. But a synthesis problem only requires the reactions, okay? I would not require a mechanism for those, but you're just asking in general, right?
Yeah.
So yeah, I will not ask a free radical mechanism on the exam, and epoxidation is off. So yeah, you'd have to be able to draw an E2, and that's chapter 7. So again, if it's escaped, chapter 7 is on exam 3 as well. Chapter 7 is substitution and elimination. So you've already seen that. I'm not going to crank it up. So you should be able, right? A lot of you missed some points on that on exam 2. You should be able to figure out what you missed and come up with it. Yeah.
There are no review sessions between Wednesday and the exam, right? Tomorrow's the last one.
There's none scheduled at the moment, but there probably will be. All these things basically depend on whether I can get rooms or not. And it's this, oh hey, did have a question.